Hello, my name is Rachel Kadar, and today we're going to talk about Introduction to Ultrasound Physics. I have no financial disclosures. Today we're going to talk about the physics of ultrasound. We'll review knobology, or the different knobs you can use. And most importantly, we'll differentiate between the different modes of ultrasound. So we'll talk about 2D or B mode. We'll talk about M mode or motion mode. We'll review spectral Doppler, talking about both pulsed wave and continuous wave Doppler. And then we'll touch briefly on color Doppler and tissue Doppler. So let's review the core principles of ultrasound. There are a couple terms we'd like to review. So amplitude is going to be the height or the brightness or how loud that ultrasound beam is. So ultrasound is a wave that travels through different medians. And that wave has both a frequency and a wavelength. The frequency is going to be the number of waves in 1 second, and this is measured in hertz. So diagnostic ultrasound is much higher frequency than our hearing ultrasound. It's going to be at 1 to 20 megahertz. The wavelength is going to be the distance from peak to peak, and this is measured in meters. We'll talk a little bit on the next slide about propagation velocity, but that is how quickly the ultrasound wave travels through a medium, and that can be different based on what it's traveling through. The point of the physics is to point out that these two things have an inverse relationship. So if you have a high frequency, you're going to have a short wavelength. And these ultrasound beams are used to look at shallow structures, but you'll have a very high resolution because of that very short wavelength. Conversely, if you have a low frequency, this will have a long wavelength. These long wavelengths can travel deep into the body and look at deep structures, but your resolution will not be as clear. You'll have a poorer resolution. So how does ultrasound actually work? So the transducer on the end of it has these piezoelectric crystals, and you'll have electrical energy come to the transducer, and the piezoelectric crystals will convert that into mechanical energy. So it will make this ultrasound wave, which is moving through the medium. So the crystal, this piezoelectric crystal, will send the images or send the wave, and then it will pause, and then it will receive the wave back as like an image and interpret it as an image. Overall, you essentially have a very short pulse and a really long wait time. So as you see in this picture, the ultrasound beam goes out, it hits your object, it ideally is reflected back to the transducer, and the transducer can then interpret an image. As you note here, though, some of those waves are actually transmitted through the object. Remember, we talked about propagation speed. That's how fast that ultrasound wave is going. How fast it goes is going to depend on the medium that the sound is traveling through. So ultrasound waves don't travel very well through air or lungs, so it goes pretty slow through there, 500 meters per second. 1540 meters per second is what it travels through soft tissue. And I put that in red because if you ever take boards, that's the number they want you to know. And it travels very fast through dense tissue such as bone. So it travels at 3000 meters per second through bone. This is important to note because when we talk about artifacts, we often assume that the propagation speed is the same through all tissues when we look at ultrasound images, which of course is not always the case. So in ultrasound, time equals distance. So if you see here in my picture, I have an ultrasound transducer. Here's my indicator over here. This is the object that I'm looking at. And this is my picture on my ultrasound screen. So it lines up with the transducer image over here. You can see I have 3 objects here. The object that is closer to the probe is going to end up at the top of the screen. This is the object that it took less time for the images to come back to the transducer. Objects that are further away will end up in the far field. So when we look at our image, we have a near field and a far field. Near field is at the top of the screen or closer to the transducer. Far field is going to be at the bottom of the screen, further away from the transducer. Some terms that we should know is echogenicity. So when we talk about echogenicity, it's the different shades of gray. So at one end, we have hyperechoic or bright white. At the other end, we have anechoic or black. And in the middle is, or gray, is kind of an isoechoic. Hypoechoic is a nice term that can be used when comparing two different structures. So a structure that is hypoechoic compared to a different structure. Hyperechoic, the bright white, that's when all of the ultrasound waves come back to the transducer. So that transducer gets a really high wave amplitude or high brightness. Examples of things that do these are bones or stones. On the other hand, anechoic, that's when none of the ultrasound waves come back. So it's lacking echoes, hence the word anechoic. Things that are anechoic are fluid, such as urine, blood, or bile. Now, when these ultrasound waves go out and hit an object, they can do lots of different things. So when we interpret images, we're interpreting the images usually that hit the object and that are reflected back to the transducer. But as you see here, ultrasound beams can also hit the object and be scattered about, never make it back to the transducer. They can be refracted, meaning they hit the object, but they continue to travel, but at a different angle. They can be absorbed by the object itself, or they can transmit through the object and go further to deeper structures. Here are the three probes: the linear array probe, the curved array probe, and the phased array probe. You can see also the way that these ultrasound beams kind of exit the probe, specifically noting that the phased array probe on your right, the ultrasound beams come out kind of together and then spread out. So it's really nice to get into or in between the ribs. So the linear array probe, as we'll talk about in the next lecture, is going to be our high resolution probe. Doesn't travel very deep. I use it for vascular access, my DVT ultrasound, and pneumothorax. Curved array probe I use for fast exam or gastric. And then the phased array is best for the cardiac exam or when looking at lung parenchyma or pleural effusions. Again, we talked about resolution versus penetration. So resolution is the ability to differentiate between two objects on the screen, kind of how clear your picture is. Penetration is your ability to visualize deep structures clearly. So how deep into the body can your ultrasound go? Our abdominal probe is at the top here, and our vascular access at the bottom, showing that the abdominal probe has the greatest penetration, but also lower resolution. So I would also use that if I'm looking at the aorta. And again, if we take this back to the physics of it, the abdominal probe has ultrasound waves that have a lower frequency and a longer wavelength that look at deep structures, but a poorer resolution, whereas that vascular probe is going to have a higher frequency, a short wavelength to look at shallow structures, and a higher resolution. We can also talk about axial versus lateral resolution. So axial resolution is how clear are two structures that are parallel to the ultrasound beam. And so if you have a higher frequency, you're going to have a better axial resolution. You're going to be able to see those structures more clearly. Versus lateral resolution is when you can distinguish between two structures that are perpendicular to the beam or essentially next to each other. This is going to be best at the focal point. The focal point is where those ultrasound beams kind of naturally tend to come together at a certain point on the screen. And so we can adjust that focal point if you have a more advanced ultrasound machine. But a lot of the ultrasound machines we'll be using, the Sonasight, for example, has an automatic focal point based on the depth. So this is one of the reasons it's really important to optimize your depth when you're doing ultrasound so that your focal point is also optimized. It can make your image much clearer. Now we're going to review the different modes. So there's 2D or B mode, there's M mode or motion mode, spectral Doppler, we'll talk about pulse wave and continuous wave, color Doppler, and tissue Doppler we'll touch on briefly. So B mode, it's called brightness mode, or it's really just 2D imaging. It's what you think of when you think of ultrasound. It can be still images or movies, but it's when you put the ultrasound probe on the chest and the the ultrasound waves go out, they hit the objects, they come back to the transducer, and you get an image. So again, that image can be a video. If we're doing any cardiac ultrasound, we'd always want to get a video. Or if you're just taking a still image, for example, you have a pleural effusion or you want to look at A lines or B lines, you can do still images for those. M mode is motion mode. And what this does is when you hit M mode, a little line will come up on your ultrasound screen. So here you can see it right here. And this is going to take this line and it's going to tell you all the motion that's happening along this line. And it's going to plot it on this graph here where distance is your y-axis and time is your x-axis. And it's going to show you all the motion in that line. This is really great for intracardiac movement. So for example, if you have a valve that's moving very quickly and you want to look at what that valve is doing. So if you look, this black or anechoic area, you can kind of see it up here. It's a little isoechoic just because you have some artifact here. That would be the right ventricle. And then this black or anechoic area here is, excuse me, kind of the left ventricle, a little bit maybe seeing the left atrium. And then this line here, this is actually that anterior leaflet of the mitral valve. And so you're seeing the E wave and the A wave. So this M mode or motion mode is allowing you to look at that motion of the anterior leaflet of the mitral valve in this instance. And again, it can look at the motions of a lot of different valves, which is really helpful. Now we're going to move on to the Doppler effect. So the Doppler effect or the Doppler shift is really that idea that there's a change in the frequency of sound when there's motion between the source of the sound and the receiver of the sound. So I'm sure we all remember in physics, the typical example is the ambulance. And when that ambulance is moving towards you, right, you end up with a sound that has a higher frequency and the sound sounds like a higher pitch, right? Whereas if the ambulance is moving away from you, those sound waves become longer and you have a lower frequency, which we can hear by a lower pitch. So how are we going to use this effect, this Doppler shift in ultrasound? So we're going to use it to calculate the velocity and specifically the velocity of blood. So we calculate the velocity of blood using this Doppler shift, and the equation is up here in the corner. And when we do this, we end up with either a positive Doppler shift or a negative Doppler shift. So if you see right here in my picture, my ultrasound beam is here, and the blood is traveling towards the ultrasound beam. So we are going to end up with a positive Doppler shift. So when we look at the velocity of that blood, it's going to be seen as higher because it's moving towards you. The source and the receiver are traveling towards one another. And when we interpret this in our ultrasound, this is going to be a deflection above the line because it's a positive Doppler shift. Whereas in the bottom picture, right here, we actually have a negative Doppler shift. We align our transducer with the blood, but the blood is traveling away from our transducer. And so we have a lower frequency. The source and receiver are traveling away from each other. The source being the blood, right? And the receiver being my ultrasound probe. And so this is going to be interpreted as a deflection below the line. So when we're using ultrasound to calculate the velocity of blood, we're going to align either directly where the blood's coming toward us or coming away from us. So why is this angle of the transducer important? So if you look at this equation right here, we have the cosine of theta. When we measure this blood or the velocity of blood, we want to measure parallel to the blood flow, where the blood is either coming at us or away from us. Because theta, this is this intercept between the ultrasound beam and the direction of the blood. This is the angle right here. So the cosine of theta, which is what's in this equation, the cosine of 0, so you're directly with the blood, or 180, directly opposite of the blood, is 1. And so if we are not totally parallel to the blood flow, we will end up getting a number that's not 1, and we can't ignore this. We want to essentially ignore the cosine of theta in our equation. So if we can't, then we can't ignore it. But more specifically, if you look at this picture, we have A, we're relatively parallel to the flow of blood. Blood is going towards the transducer, so you get a positive Doppler shift. And so this will measure here the velocity of blood. On the other end, D, you're anti-parallel or parallel again in a different way, depending on how you want to think of it, to blood. and the blood is traveling away from the transducer. And so we have a negative Doppler shift. If you look at B and C, we're almost perpendicular. And so you can't really measure that velocity of blood appropriately. You underestimate the velocity of that blood when you're not parallel to it. And so when we do certain ultrasound images, we have to do them in certain windows or certain angles when we're using Doppler sometimes in order to get an appropriate measurement. Now, when we do spectral Doppler, when we want to look at the velocity of blood, we have two different options. We can do pulse wave or we can do continuous wave. And overall, the idea is that the pulse wave will transmit and listen, and transmit and listen. So it has what we call range specificity. Whereas continuous wave Doppler, that actually has two crystals, it's continuously transmitting and continuously listening, but you have range ambiguity. What does that mean? So in continuous wave Doppler, we're constantly sending and constantly listening for the velocity of blood, but we're not really paying attention to where that velocity is. So we don't know where the velocity of blood is along my line, but I know the velocity. Whereas in pulse wave Doppler, I'm listening for the velocity of blood at a specific location. So let's look a little bit more. So pulse wave Doppler has one crystal, and we listen at a fixed depth. So this example up here, this is an apical 5-chamber view. You have your left ventricle, left atrium. We can't really see the right atrium. The 5-chamber is we have the LVOT, or the left ventricular outflow tract, the aortic valve, and the aorta. So the aorta is that 5th chamber. And this has a little sample gate that it's putting in the LVOT. So we put it in pulsed wave. We put that in the LVOT because we want the velocity of blood in the left ventricular outflow tract. We want to know the velocity of blood at that specific location. You have one crystal, it's going to listen at that fixed depth, and it's going to give you the velocities along that time, at that specific location over time. So again, this is velocity over time. As you go through the cardiac cycle, this will tell you the velocity of blood during that time, right? So when you're not in systole, there is no velocity of blood because no blood is necessarily going through that left ventricular outflow tract. This is a negative Doppler shift because the blood is moving away from my transducer. And if you look at this picture, this is what we call a scooped out waveform. It's black in the center because here, this line is showing us the velocity of blood. This is traced because when we talk in our further lectures about obtaining cardiac output, we can trace that to look at our stroke volume. But for now, I just want you to recognize that this is using pulse wave technology to look at the velocity of blood at a specific location. Alternatively, we have continuous wave Doppler. So this is actually an apical long axis view where they have continuous wave Doppler across the aortic valve. This is, again, across the aortic valve here as well. And so in continuous wave Doppler, you have two crystals. So they're constantly transmitting, they're constantly listening. And so again, that blood is going away from your transducer. So it's a negative Doppler shift. But when you look over time, because we're constantly sending and constantly receiving, your waveform here is filled in. And so it's all filled in. And so how well filled in will also kind of tell you how good your positioning is, both of your ultrasound probe and of your line that you've put there. And this is helpful for detecting really high velocities. Pulse wave cannot do high velocities. So this is when you don't care where along that line the velocity is because you know you're looking at the velocity, for example, across the aortic valve. I know that the maximum velocity across my aortic valve is at that stenotic aortic valve, but I really want to know how high that velocity is because that's going to tell me my degree of aortic stenosis. So again, this would be continuous wave Doppler, for example, across an aortic valve or any other valve to give you that high velocity. So again, the difference between pulse wave and continuous wave. Pulse wave measures the velocity at a specific location. Continuous wave will measure the fastest velocity along the Doppler beam, but it won't tell you where. Pulse wave will send a pulse and listen for it to return. Continuous wave is constantly sending these pulses. Pulse wave does your lower velocities. It can't really do those high velocities, whereas continuous wave will look for high velocities. So when you're looking at the velocity across a valve, pulse wave is going to be a scooped out envelope, where it's going to be anechoic or black in the center, whereas continuous wave is going to be that nice solid filled in envelope. So how well scooped out and how well solidly filled in will also tell you if your positioning is accurate for both of these when doing these maneuvers. Briefly, we're just going to talk about color Doppler. When you put color Doppler on, I always remember the BART, if you ever travel in San Francisco, blue away, red towards. So what it's going to do is it's going to look at your image right here, and it's going to say, if it's a positive Doppler shift, if blood is going towards the transducer, it's going to make that red. If it's a negative Doppler shift, it's going away, it's going to make it blue. And then you see if those velocities get really high, or if you have, turbulent velocity, you're going to get those yellow or green colors. That's when we start talking about aliasing. So sometimes this can be helpful. I'm not always looking at whether it's red or whether it's blue, but I'm looking at, is there blood flow and how do I get turbulent blood flow? So when I'm looking for mitral regurgitation, for example, or I might just be looking for the color Doppler to see, is there blood flow regurgitating back into a chamber when I wouldn't expect it to be? And then tissue Doppler, we're not going to talk much about it, but I just want you to see kind of what it can look like. We said when we look at spectral Doppler, we're listening to the blood, the velocity of the blood. This is going to listen to the muscle and the tissue, and this is often used in diastology, but we're not going to use it much in POCUS, but this is what it might look like. So we're going to end with just talking a little bit about image optimization when you're ultrasounding, which I talk more about in my next lecture. Well, first of all, we want to make sure we choose the correct transducer. So whether it's the vascular probe or the cardiac or the abdominal probe, we also want to make sure we choose the correct mode. I put that in red because it's really important that we put it in the appropriate mode. So if you're doing cardiac, make sure it's in cardiac mode and the indicator's on the right side of the screen. Versus lung mode, it'll be to the left side of the screen. But lung mode, what we'll talk about later, we look at artifacts to gather information about the lung, versus the cardiac mode tries to get rid of all those artifacts. So if you're doing lung ultrasound, you really need to make sure it's in lung mode or at least abdominal mode, but not in cardiac mode. Versus if you're looking at the abdomen, for a fast exam, you want it in abdominal mode. So just make sure it's in the appropriate mode to look at whatever it is you want to look at so that your image is optimized. We're always going to start with window shopping. So if you're looking at the heart, you're going around the chest trying to find that best window to look at the heart. Or if it's the kidney or whatever you're looking at. Depth, we want to make sure we optimize that depth. So put what you want in the center to 2/3 of the screen. Gain, that's going to be that brightness and darkness. So you can adjust the overall gain. That'll change the gain over the entire image. Or TCG is doing the gain in a specific area. So you can often increase the brightness or darkness in either the near field or the far field. And then there's also the focal zone. So remember we said lateral resolution is best at the focal zone. Some ultrasound machines, you can adjust that focal zone, but on our Sonocytes that we're going to use, it's automatically adjusted for you based on the depth. So that's why it's really important to put that depth to optimize what you're looking at, because that's going to make your image the clearest. Thank you very much for your time, and I hope you've enjoyed this video.